It's okay.
Good. Okay, now we're recording. Yes.
Oh, okay. Awesome. So, hey everyone, and first, thanks for the invitation. I'm really glad for the chance, and I was thinking about a topic that I had a couple of opportunities to discuss with people from the department here, from the Technion as a whole, but also before Corona, and when we sat in the H bar. We had a couple of interesting discussions on these topics, and I thought it would be interesting to bring it up here. I'll go into this topic, but I'll say a few things before this. That we are a group now almost 3 years at the Technion, and over those years we worked really hard to start our lab, and I think this was a really beautiful team effort, and I'm really happy that we are starting to see over the past year the first results that we're getting from the lab and from what we've done. So I'll also have a chance to show you a little bit on what we were doing and how it connects to this question that I want to make the focus of the talk. And this is the question of the electron wave function and how it behaves when radiating, and especially whether we expect to see the electron wave function collapsing when it's emitting radiation. And I'll discuss both the scenario when the radiation is spontaneous and when it's stimulated, and we'll see how different experiments that we're doing are having this question coming back again and again in many of the experiments we're running. And that's will be the focus of the talk. As a group, we're doing both theory and experiments. We're doing a lot of what we're doing is about applications of quantum electrodynamics, and you'll see how this connects here in different places. But before I go into the details, I want to say one more thing, and this is that I want to give this talk in memory of Mark Stockman, who passed away last week, and he is famous in our field for contributions in plasmonics. But on me, he had an impact on very different areas, actually. In conferences, he was always this go-to guy, go-to person for first debates, for the wildest ideas. And I especially remember discussions with him on the collapse of the wave function in the presence of strong fields, which is a topic that he was an expert in. For example, when does the electron wave function collapse in high harmonic generation? And this is something that also influences my thinking on the topic and what we'll discuss today. So I'll start by from an experiment that I'm sure you're all familiar with. This is the double slit experiment. And I'm going to present a modified version of it, or actually a few modified versions of it. But let's first recall this part. So if we have an electron source that emits an electron wave, and that wave goes through a barrier with two slits, we expect to see the wave of the electron then interfere on some screen down the road and see some interference pattern. This is a beautiful demonstration of the wave nature of electrons. And actually, the first experiment that showed this, I don't know if you're familiar with this, but in the 70s in Italy, there was an experiment done inside an electron microscope. What you can see here is a series of lenses. Those are electromagnetic lenses that can collimate the electron beam. And then at some point, the electron beam is split to two and then brought together and interfere. And what you can see here is a really beautiful example. It was, by the way, voted in the beginning of the 2000s to be the most beautiful experiment in physics by the readers of physics today. And it is, I think, beautiful experiment. You can see on the screen individual electrons hitting, originally individual spots, and over time how the fringes are appearing as the result of many, many measurements. And that's an example of how we can see the electron wave nature in a microscope, and also how we can see that electron wave nature collapses on the screen. And I think those two things are one more reason to look into electron microscopes, and we'll come back to this later. But let's look back into this double slit experiment and now recall that what I think is the more interesting part of it is not the fact that the electron is a wave, but the fact that when we come and measure the wave, look at it in one slit, we no longer get the interference pattern, right? And that's very famous for where the act of measurement alters what's happening in physics. And that this is all about the measurement process that's at the heart of the problem. And what is really happening when we measure. And for this reason, I want to bring up another Gedanken experiment, a slightly modified version of the double slit. Imagine that we're trying to define now what is the act of measurement. So we put a piece of material let's say a piece of phosphor screen that glows when the electron hits it. And we will put two of them and then ask what happens to the light emitted from this phosphor screen, but not look at it right away at it, but look at another screen down the road and let the light from the phosphor screen interfere on the screen. And now the question is, what's going to happen from this kind of experiment? So the electron is causing light emission. That is in some way the act of measurement, but you can say, well, we didn't really look at the light right at the phosphor screen, we look at it down the road, and then it could potentially interfere on the second screen. So you can say, where does the collapse of the wave function happen? Is it happening up here or down here? And that's a question that I remember having and formulating a few discussions over lunch, where we could still have it inside in Nuna. And that's the question I want to focus on for this talk and show you a few different real experiments that can give us insight on what's happening here. Because I heard first opinions about what's happening in this experiment, and I'll tell you what we know so far. And I think that's quite a lot. So that's the question we'll take with us for the rest of the talk. Is the electron measured when it's emitting radiation here? And there are generally two options, right? There is first, the electron collapses here and then radiates. If that happens, then we'll see no interference on the screen because it emitted from only one of those 2 points. Or maybe it radiates from the entire wave function, and then the actual act of measurement only happens on the screen where we record it down the road. And what we'll see in practice is that depends a lot on the act of measurement itself, on what is the material that's going to emit radiation. And to understand the full picture here, is we can always think about the entanglement that's going to be created between the electron and the emitted photon or photons that are going to be created here. And through the full picture of an entangled state, electron and photon, we'll be able to tell whether there is an interference there or not. And actually, the answer is that it depends. It depends, and we can see experiments that do both. Before I go into it, I want to say a few words about the electrons, because we like doing physics with free electrons, and we do quite a lot of different things with free electrons. And in many of them, we see this act of measurement on the electron wave function, but not in all of them. And I think the free electrons are really beautiful for doing physics for a lot of different reasons. This is, of course, happening for many, many years, but there are a lot of new things we can do with them. And I want to show you a few examples of the kind of things we're doing in the lab before I focus on the act of measurement alone. For example, free electrons are very famous for creating radiation. They are part of synchrotron sources and free electron lasers. And this is something that we've been using recently to make X-ray radiation from van der Waals materials. We can use free electrons for optical microscopy, for looking at the near field at resolution that we cannot do with regular optical microscopes. And we know how to today shape electrons in the form that carry the information for qubits, including the interesting algebra of the qubit, that is non-commutative operations. This is so far a theoretical idea that we're pursuing. I'll show you more on how we can make attosecond electron pulse trains. So we shape the electron into attosecond pulses. This is something that is now getting a lot of attention in the community. And we can also use electrons as probes inside electron microscopes to look into other qubits. For example, place a quantum dot and ask, what is the decoherence rate of that quantum dot? And look at the individual quantum dots and measure their properties. So those are all examples of things we can do with free electrons. And many of them are possible because of the unique setup that we've built at the Technion that's located inside the electron microscopy center in the materials department. But I think about half of the ideas here are actually theoretical, pure theory, and still they are inspired by advances in the lab. And I'll go into a few of them down the road in this talk. But if I want to zoom out a bit and ask what's really interesting in this experimental platform we're playing with. So those are pictures from, actually the first one here on the left is from October 2018. This is really the beginning of the construction of the lab. And that's how it looked like a few months after. And really, if I summarize why we like this platform for electron microscopes, there are two things. One of them is that we can see quantum effects in areas that are, for many years, were considered classical. If we think about electron experiments, for example, electron acceleration or electron radiation sources free electron lasers. Those are big facilities that treat and model electrons as classical creatures. And we can now, thanks to the electron microscope and the very precise methods of measuring things there, we can see quantum effects in systems that were, in experiments that were considered classical for many years. And the other one is that free electrons allow us to look now with this precision into experiments that are completely analogous to what we can do in atomic physics. We're looking into effects that are traditional, like Purcell enhancement, or the ideas like lamp shifts, are ideas that all emerge from atomic physics, and we can now revisit them with free electrons. And I think that you'll see those 2 points, those 2 ideas come back later in the talk as the essence of what we like to do with free electrons and what we can achieve when the measurement tool is so precise. So I'll use this to keep in mind a picture of an experimental setup like that, but we'll apply that now for the Ganacton experiment I mentioned before. So we're looking into different experiments that can implement a type of measurement where the electron is interacting with light or emitting light, and that causes it to be measured. Okay, and I'll discuss a few experiments that give insight on this problem. The first one is what happens when the electron is now illuminated by light. Okay, illuminated by light, what will actually happen here is another form of radiation. This will be stimulated radiation, where the electron is excited by light and then emitting more of it. And we can do that on, for example, one or both of the slits. And that's giving us to complete a picture of what's the measurement on the electron wave function. So what can we do to implement that? Let me rotate this a little bit and try to look at an analog of this double slit experiment, but in the time domain. This is an experiment that was the most natural for us to try, where we have our electron actually very long, coherent, along the direction of motion. The electron pulse is extended, it is coherent over a few hundreds of femtoseconds, and that allows us to interact along the z direction, along the direction of motion of that electron with light in different locations. So this is a type of double slit experiment that we want to do that is now rotated to happen in 2 places in space along the direction of motion of the electron instead of transversely. And to make that kind of interaction happen, you'll see in a moment why, we're going to use a prism to help us couple the light into the electron and mediate the interaction between them. Or more specifically, this prism is going to do the following. We'll have a laser pulse coupled from top. It will go through Snell's law, and then through total internal reflection and out to the prism. And this is a simulation of that field, how it looks like. You can actually see the red and blue here are the electric field component polarization and how it oscillates. Now we illustrate the electron as this extended long sphere, because it is actually an extended long wave function. And we also align it to move in parallel, in synchrony with the velocity of the oscillation of the field. This is what we call the phase velocity of light. Okay, and that kind of experiment is what we're going to show in a moment. But I want to say the following, which is that the field here, when interacting with the electron in this shape, can accelerate the electron, right? And this is something we know and we expect. The fields can act on the electron and push it down or decelerate it the same way. And then a question that is analogous to the one we asked before is, what happens to the accelerating electrons when interacting with the field? Does the electron collapse and then accelerates? So we expect different locations to be acting in some probabilistic manner, or can we get acceleration or deceleration of the entire coherent wave function as a whole? Okay, and we'll see in a moment the answer to this is actually not very hard. But just one more simulation of this type. The actual experiment looks a little bit different. It looks more like this. This is a more true scenario where the actual electron is coherent and long, but not that long. It is limited in coherence, and the pulse itself is also quite short. Okay, so of course things are not that easy always. And still, we'll take that into account when we have enough coherence to be able to look into this question that I asked. So how is this going to happen? And this is an experiment led by Rafael Dan and Sal Nechemia from my group. We are looking into an electron, and now we are zooming in on the point of interaction. You can see on the left here, where the laser pulse is going to go through this total internal reflection, but a little bit of the laser that is reflected is always going to leak out. This is the evanescent tail that is, we also see in optical fibers and other methods for guiding light. And that evanescent tail is the one that's going to interact with the electron. We need to do that because the electron does not pass through enough of the solid material. So we're trying to bring light to interact with it, and still to do that without bringing the electron into the material itself. And what we get then is that the electron, extended electron, is seeing the oscillatory shape of the light, and that causes different parts of the wave function to see different types of the field, different directions of the field polarization, for example. And the result of an interaction like this is going to look the following way. We have our electron measured in the energy domain. We have an electron energy spectrometer that tells us what is the electron energy distribution. And the original one looks something like this. We have a narrow peak at about 200 kilovolts. That's the electron. That's about 70% the speed of light, and it's the width of about 1 electron volt. So that's how monochromatic, how monoenergetic the electron is. And after interaction, we're going to measure the electron energy again. And what we find is the following picture. You see that as a function of energy here, and this is whether the electron lost energy or gained energy, we see a bunch of peaks. See this oscillatory behavior with the distance between peaks being exactly the energy of a single photon. You can think about it in a few ways, but one of them is to think about the double slit experiment. We see an interference of light that is typically taking us by patterning the surface, putting two slits, and then looking into the far field as a function of angle. So, and then seeing the interference. When we're looking at the interference from 2 points in space, we see those patterns. The analogy of this location to momentum transform, the Fourier transform, is going to be time to energy. If we bring an oscillatory field to interact with the electron, the Fourier of that will be the energy domain. And that's how we see the interference pattern in the energy domain. And we can really think about it this way. When we modulate the electron in time, what happens in the energy domain is going to be a modulated electron, as long as the electron behaves as a wave. And that is indeed what we see experimentally. We can also think about it in many other ways, like think about the electron as if it absorbs or emits individual photons in order to change its energy by this discrete, into this discrete ladder of levels, of energy levels. And both pictures are equivalent. And we'll see also the theory in a few slides. But the important thing to understand here is that the electron behaves as a wave. It behaves as a wave just like the electron in the double slit behaves as a wave. When we modulate it in time, we see how it's modulated in energy. And this is something that in order to achieve in an efficient way, we can think about as if the electron is just a wave. We never think about a word collapse. And we find that part of the same electron accelerates and parts decelerate. Different points in space see a field that pushes the electron down, other parts see fields that push it up. This creates a coherent electron energy comp in practice. The same electron is now going to occupy many, up to a few thousand energy levels, and they're all occupied by the same electron. And to make this so efficient, and this is the challenge in that experiment, we need to match the electron to interact with the light for the longest distance possible, while moving with the same velocity of light. This is what we call phase matching. And how it looks like, if you think about the electron here, first on the left side, as moving through the field, you can see that the same part of the electron that sees a decelerating field will keep on getting decelerated, while other parts will keep on getting accelerated. That's because the phase velocity of the field is exactly synchronized with the shape of the electron wave function. So the same parts will go on either accumulating more energy or losing more and more energy. While if we do not match the velocities precisely, even a small change, the same parts that originally accelerated are now decelerating after a while, and the desynchrony between the velocity of the two parts of the two waves, the light wave and the electron wave, will cause the strength of this effect to diminish. And that's also how it looks like experimentally.
I have a question.
Yeah.
So if you have a part of the electron that's getting accelerated or decelerated, then by definition, if it started out at the same phase speed as the light, when it gets accelerated, it's no longer at that speed, right? So it wouldn't keep seeing the same phase all along.
Right. So you're saying basically the picture, even the picture on the left, is not really perfect, because once the electron starts getting energy, it will slip away from that field. And that is a correction that we should consider, but it's a second order correction. If you think about electrons that are at about 200 kilo electron volts, and you add even 100 electron volts to them, it is still a relatively small correction to their energy. So this slippage is something that we can consider at second order, and not as the leading effect. But right, this is, if the interaction is strong enough, at some point things are going to get distorted much more heavily.
Thanks.
So if we compare what happens when we align the velocity and we actually work not at 200 kilovolts, but at 207.2 kilovolts, then we see that the interaction is pretty wide. While if we change the energy a little bit, this is what we call phase mismatched, or we're not matching the velocities perfectly, we see that the width of the electron change in energy drops significantly. And that is the difference between matching it precisely or not matching it. We can achieve that. And now going into how this is actually implemented in the following way, we actually need to make the electron phase velocity exactly equal, the light phase velocity exactly equal the velocity of the electron. And that's something that you can show happens when the velocity of the light is modified through that light moving in some angle. That's the reason we need to use the total internal reflection here. We need the light to arrive at the electron at a precise angle, theta, that satisfies this equation. Cos theta is the speed of light divided by the velocity of the electron times the index of refraction. Without having the index of refraction here, like in free space, that can never be satisfied. So we actually need to use the prism in order to have the index of refraction there. And then we can satisfy this equation. That's exactly the formula that is also called the Cherenkov angle formula. And that's related to the Cherenkov effect. What we actually have here is an analog of inverting the Cherenkov effect, or it's called the inverse Cherenkov effect. And what we've done here is a quantum version of it, when we actually modify the electron as a wave function. This is an experiment that was done classically in an electron in another kind of electron microscope a few years ago by the Peter Homelov group in Germany. And this is how it looks like. We actually use a prism that is 0.5 millimeter in size, which is enormous on the scales of the electron microscope. It was the main challenge here that Raphael solved, is to align it so the electron can graze the surface of the prism, stay at a distance of less than a wavelength away for a duration of the entire size of the prism, which is about 500 microns at a distance of less than half a micron. And this aspect ratio of about 1 in 1,000 was a major challenge experimentally. To do that, we actually put this entire prism inside the electron microscope. And the electron microscope now has a couple of ports to couple light into it. We have two that are important here. One of them is a UV pulse that is exciting the electron pulse, deciding when the electron pulse is excited from the tip. The other one is the laser pulse that is excited the prism and interacting with the electron down the road. That electron then comes out from the interaction area and goes down to the electron spectrometer. That is, through a magnetic field that bends it in 90 degrees, sends the electrons at different angles as a function of the momentum of that electron, and that gives us the energy distribution of the electron. Okay, that's the system that we designed here, and is called the ultrafast transmission electron microscope. And I'll say a few words about it down the road, but as an acronym, this is the UTEM, and I'll say UTEM later on. So for us, this is not just an experiment to look into how light interacts with the electron wave function, but it was really the question of what happens to the interaction of this type, this Cherenkov interaction, when the electron wave function is critical, when we have an electron that is coherent enough to shape the interaction this way. And this is the first time that anyone sees wave function corrections or quantum corrections of any type to the Cherenkov effect. And that's what got us excited about this experiment to start with. And what we find is that when we look into the electron energy distribution, it is actually extended over a very wide range. So wide that it was not simple to measure. And you can actually see the energy axis here spanning from minus 200 electron volts to 40 electron volts, and it goes on both sides. Altogether, we had so far about 1700 electron volts bandwidth for this electron. We expect to get much beyond that soon. But that means that the same electron is now occupying energy levels in a discrete way over a range of few thousands of electron volts. And I think this is a very exciting creature that was created here. So what is the theory behind the scenes? I already said that the electron is acting as a coherent wave function and is not modified, doesn't collapse. That means we can write the Schrödinger equation for this electron and put in the potential, the electromagnetic field, as a vector potential with the Coulomb gauge. It means we can ignore the scalar potential in this case. We also need to add relativistic corrections, and this is not very hard to do in this case. And to solve this equation, one can use a couple of very elegant tricks. For example, the fact that the electron is moving in a very directional way means we can apply a paraxial approximation that allows us to simplify the equation quite significantly and look into an analytic solution. And how this looks like in the end, there is one dimensionless parameter, we call it G. This is the interaction strength that can be acquired quite relatively simply by looking at the Fourier transform over the electric field. And then, by the way, if you neglect the change in time, the dynamics of the wave function, you get a simpler equation that is what was done in 2010 by two groups in parallel, Garcia de Abajo and Sancté Park in the Well group, to develop a similar theory to a simpler kind of interaction. That was the first time that this type of approach was applied to the electron interaction with electromagnetic field. But in our case, in a more general way, with a general wave function, which we need for this interaction, we can use this G that we defined and then substitute it into the following density function. This is actually a probability density for the electron as a function of space where it hits next to the prism, as a function of energy and the delay between the pulses, arrival of the pulses. And what we find is that this G is the only parameter that's really necessary in order to describe this discrete electron energy, which looks the following way. It's the sum of delta functions in energy multiplied by coefficients that all go like Bessel functions, with the argument of the Bessel function being this G dimensionless parameter. So we can completely analytically solve that, and you can see how this is equivalent to a quantum walk of a quantum walker going on a discrete ladder in 1 dimensions. But that's something that can be seen in about a line of calculation and is related to Bloch oscillations and to other effects that we looked into theoretically. To match this in the end, we need to do one more step. And that step is that the electron carries some incoherent part to it as well. The electron is not really a delta function in energy. It has some width. So what we need is to convolve this density with another one that is describing the incoherent broadening of the electron in energy and in time. But with this convolution, we get the final result that is describing the experiment beautifully. Now, I want to say one word about this. In the following way, we were looking into how this compares to a classical description. If we think about that same electron as a point moving in space, interacting with an electromagnetic field, we can use the Lorentz force, for example, as a way to describe the interaction. And then one can actually use the exact same derivation here with only changing one element. This is the coherent density here. It looks like a sum of Bessel functions. And if we replace that by another classical distribution that looks like this is 1 over square root of an expression that contains the energy change of the electron, this W, which is also dependent on the same G that we defined before. That gives us exactly the same distribution. And if you look at it, it's like a discrete points in space versus a continuous one. And that's this correspondence, I think is really elegant. For example, you can see it here. If we look at the data here, that's the orange, versus the theory in blue, the classical theory will follow the same line generally, but looks like the average, while the quantum theory gives us the exact oscillations that we are following here, that are exactly separated by h bar omega. Okay, and that's how we can really get a more precise description of what's happening in those experiments. And of course, we need a quantum theory to describe it. Okay, so let me go back from here to this Gedanken experiment that I described, because so far we saw that the electron remains a coherent wave function. That's why we can just put a vector potential of the electromagnetic field inside, and that's all. But how do we know when it is legit to just treat the light field as a potential in Schrödinger's equations? when is it legit to just do that and ignore any thought of collapse or anything like this? Okay, why is it legit to do that in the first place? And the short answer is that it is true almost as a coincidence. Since the laser light is a coherent state, the electron doesn't get entangled with it. And that means that we can think about the electron as remaining coherent with no effect of collapse in any way. And that's almost a coincidence. And I want to say a few words of why this happens before I go away to regimes where this is not legit anymore. Okay, and then writing the Schrodinger equation with a time-dependent potential will not be legit. And to understand that, I want to think about the electron and the light in a language that is much more fundamental and basic. We know a few kinds of quantum systems when we're teaching undergrad courses on quantum mechanics. One of them is the two-level system, that is describing a qubit. Another one is the harmonic oscillator or the quantum harmonic oscillator that is, for example, describing bosonic fields or a photon. And I want to introduce a third one. When we're working with our free electrons that are also relativistic in energy, we can think about them, and this is giving us a perfect perfect explanation to all the experiments we're doing, as what we call the free electron ladder. The free electron ladder has an Hamiltonian that looks like a B-W-B. It's very similar to the quantum harmonic oscillator, with this simple difference that the commutation is trivial. Going up or down the ladder does not have the square roots of n like in the harmonic oscillator, but it's just going up and down the ladder. And that description of the electron is an excellent way to look at it. And at every energetic charged particle that interacting with a quantized system or with a monochromatic electromagnetic field. And that sounds very basic. Let me show you what this means in practice for us. So if we think about those three quantum systems, we can write different interactions between them. What happens if we take the three-level systems and the quantum harmonic oscillator and write an interaction between the two? We get what we know as the James-Cummings Hamiltonian. That's the interaction of a harmonic oscillator and a two-level system. And that's what we have in a lot of descriptions of interactions between qubits, in describing NMR experiments and other things. But we can look at another type of interaction. What happens when we have the quantum harmonic oscillator interacting with the free electron ladder? That's the bottom here of the triangle is an Hamiltonian that looks like this. So there is the energy of the electron, the energy of the photonic field, and an interaction term that looks exactly the same. There is a raising of one with the price of lowering the other, or the other way around. And that's an analog of the James-Cummings Hamiltonian to the interaction of a free electron with the laser field. And that is what we call PINEM, or that's actually an acronym that is the photon-induced near-field electron microscopy. It sounds like a method in microscopy, and the reason is that it is a method in microscopy. It was originally discovered in the attempts of Ahmed Zewail to develop a new microscopy method in 2009, and later on the name stayed, even though the interaction is much more general than the microscopy method. So we call it PINEM, and we think about this fundamental interaction. Now, it's interesting to mention that the idea of writing PINEM in a fully quantized way, like I did right now, is actually pretty recent. It was not done by Zewail, and it was actually only done last year. The first paper on this is a PRL paper by Ofer Kfir as a single author. And since then, many in the community are trying to push to the regime where we actually have to use the fully quantum description of the field. And we'll discuss this more. Before I go on, I want to say that there is a triangle here, and the last side of the triangle is actually, until recently, was still empty. What is the interaction of a two-level system like a qubit with a free electron? That very basic interaction was calling for a description, and indeed, and this is very new. We know how to write a Hamiltonian. It's again the energy of two elements and the coupling term of raising one for lowering the other. But what is the actual physics scenarios that describes? So it's interesting that as of 2 weeks ago, this is no longer unexplored, and there was a barrage of papers, one by the Shanhui Fans group from Stanford, and one by us that came out on arXiv. Experiments were not done here yet, and I'm sure that over the next couple of months we'll see more work on this, and hopefully some experiments as well. But that's for another day. So we saw that so far it was legit to describe the electron experiments with a time-dependent Schrodinger equation. And that's because, as I said,
Ido, allow me to interrupt you. When you are talking about interaction of an electron with a two-level system, I think you should mention the paper that I published together with Amnon Yariv.
actually, let me add on this.
Archive paper, we made the quantum mechanical analysis
as well.
effect.
So what Avi wrote with Amnon Yariv in the beginning of 2020, this is a PRL paper that's very recent, is that interaction of an electron with a two-level system without the quantum description of the electron, but still the first one to describe an interaction with a two-level system. Maybe you're right that it's valuable to mention this first before I mention the double quantum. So back then you didn't need the double.
Paper is a quantum analysis.
Yes. The classical one that didn't need this full Hamiltonian is from this year as well, and this is Avi's paper. And then the quantum one, you're right. There are more than 2 papers on this probably, and I didn't get to read that, but there are at least 5 papers that came out over the last 2 weeks on this general area, and we will have definitely more discussions on this when we have a little bit of time to swallow all the stuff that happened.
Yes, but Ido, you should have mentioned first the paper that was already published 2 years ago, and the paper that we have now published in archive is at least as relevant as the other papers that you mentioned in green color in this transparency.
Yes, so the third paper that is also from last 2 weeks is definitely worth adding here. That's but I think we'll keep the rest of the discussion on this for after the talk. So let me go back to putting the qubit aside for the electron remaining coherent here, because so far when the laser light is coherent, the electron doesn't get entangled, and that's really what allows us to look into a lot of physics here. A lot of physics that is all captured by the time-dependent Schrödinger equation, right? And for example, the ideas of near-field optical microscopy are all here under this title. You know, the ideas of how we create out-of-second electron pulses and how we can create even electron acceleration with a quantum picture are all part of that. And I want to say a few words on the history of this, because we saw quite a lot of interest in this field in the PNM techniques over the last couple of years. So the first one was, I mentioned before, the 2009 paper by the Zoel group that showed the first observation of this idea of the electron acting in a discrete way. And the theory came up in 2010 papers, right? Back to back, almost by 2 groups. Then over the years, we saw quite a lot of contributions. I think the most significant one was by the Ropers group from Göttingen that showed how we can think about the action of the electron interaction as a quantum walk on a discrete ladder. And in the same year, there was a work by the Carbonic group using electrons here. Again, it's all under the interaction with coherent light fields to image plasmons on nanowires with sub-wavelength resolution. And we've seen many other contributions by other groups that were doing experiments in this field, and there are more and more being built over the last few years. I think one very important paper that is not always noticed is an ACS photonics paper by the Carbonic group that we also contributed to back then, that looks into the energy resolution that we can do with those structures. And here, the idea was to tune over the laser frequency and get energy spectroscopy, electron spectroscopy, at a resolution that is unachievable by any other way. Again, by the fact that the laser light is involved in the process. And very recently, we had work by our group where we looked into the coherent interactions of electrons with photonic cavities. Those are photonic crystal structures that we can image their light field, and we can see the enhanced interaction there. This was a back-to-back with the Ropers group and by Ofer Kfir there, also looking into other types of cavities in the interactions of electrons. And I think that the field is now seeing a lot of excitement around those topics. What I want to do for the rest of the talk is to show you one other idea that comes up from this that is still using coherent light, and then ask what happens when the light is no longer coherent. And for this, I want to focus on the last item here, on the fact that the electron does not collapse. What does it mean for electron acceleration? Because work on how laser light can act on electrons is something that has been of major interest in wake field accelerators in the electric laser accelerators for many years now. But in all of those, the electron is classical. And the fact that we see the electron is quantum and doesn't even collapse in those interactions is making us getting quite interested in what is going to be different in interactions of this type. So I want to show you some experiments that are being done right now in collaboration with a group called A-Chip. This is Accelerators on Chip. It's a collaboration that's led by Stanford and Erlangen in Germany, where structures that are made on silicon chips that can help guide light and trap it in a way that when bringing an electron to interact with it, can help us push the electron and accelerate it more strongly. And the first effort we did on this was led by Yuval Adiv, with measurements by Rafael Dehan and Kunpeng Wang and group and others, where the electron is now interacting with structures that we got from the guys in A-Chip in Stanford. This was a SEM picture of how the structures look like. You can see a heightened plateau. We call this the mesa. It's like a mesada structure where the structures are being fabricated. Those are silicon gratings that are aligned exactly for the laser light we bring in, and then enhancing the field so the electron is accelerated in the most efficient way we can. This is something that when looking into the electron without laser light, it looks very narrow. That's the original electron energy. And after interaction, we cannot say it's accelerated purely. We can say it's accelerated and decelerated, broadened sideways into this comb of peaks, multi-peaks structures that we see here. And that allows us to make extremely efficient interactions, like 700 femtojoule pulses can already make measurable changes to the electron energy. What is, I think, the most exciting here is that we see the discrete quantum nature of that acceleration. And that's something that requires the wave nature description for the electrons. And this is super recent. Those are structures sent by Erlangen. This is actually what's happening in the lab right now. And if we had a few more days out, I'm sure we will already have results from that as well. So those are very complex accelerator structures. Those are beautiful fabrication work that's done in this field. And we are actually measuring them these days. And I hope we'll have some exciting things to say about them. But I'll put this aside and want to say some words back on the original experiments. We said that when the electron interacts with coherent light, with coherent state light, it's not really measured. We actually can treat it as a wave function without changing much of it. So there is no real need for the idea of collapse or measurement for anything we did so far. But that's actually changing quite quickly when looking into scenarios of the following way. And for this, I want to say that so far, right, we said the electron, we can really think about the interaction of that electron and including the radiation it's emitting. It's all stimulated radiation that dominated the process so far. Stimulated radiation can really append as radiation from the entire wave function. And I can give an entire talk on this. And for example, there are theory papers on this by many authors and many important ones also by Avi Gover that are looking into the radiation, the stimulated radiation from electron wave function, where we don't need for it to collapse. But that's actually quite a weird scenario that is not very common. I'll tell you why. Because when we think about this idea of the entire wave function radiating as a whole, this is going back all the way to Schrödinger, because there is actually quite a lot of interesting discussion and work by Schrödinger himself that looked into what is the meaning of the electron wave function when it interacts with light. So when we think about electron wave function for interaction with light, what Schrödinger did originally is looking into the density, which we also teach in classes, right? This rho, this is the density of charge. And the current, also the classical current can be derived, the density of current from the slightly more complicated operation with derivatives here. And then we can take those charge and current and put them as sources for Maxwell's equations. And this logic of, well, let's take the electron wave function, derive the currents and find the radiation. This is called the semi-classical approach today. And it is how our intuition works about electrons, how we think about radiation in general. This is also how we often teach quantum mechanics. But what's pretty funny is that it is wrong to think about the electron as the density of charge. And there are many scenarios where this is just not describing reality. Still, it is widely used in theoretical descriptions of interactions of light and electrons. And it's actually also legit to use it often, like was happening in our experiments, we can really think about the electron as a density, and that was legit. So, and there is an interesting point by Feynman who is describing exactly this part, exactly this effect, where he's actually saying in one of the Feynman lectures that when Schrödinger first discovered his equation, he discovered the conservation law. This is the conservation law, the rho dt is minus dvj as a consequence of the equations. But he imagined incorrectly that rho was the electric charge density of the electron and J was the electric current density. So he thought that the electrons interacted with the electromagnetic field through these charges and currents. And then when he actually solved these equations for the hydrogen atom, there were currents moving around, and he soon found on doing a number of problems that it didn't work out quite right. And then Feynman adds that it was at this point that Born made the essential contribution to our ideas regarding quantum mechanics. It was Born who correctly, as far as we know, interpreted the psi of the Schrödinger wave function in terms of probability amplitudes. Okay, and he's summarizing that that's really the square of the amplitude is not the charge density, but it's only the probability per unit volume of finding the electron there. Okay, and that's when you do find the electron at some point, the entire charge is there. The whole idea is due to Born. And that I think the conclusion that Feynman brings is that the wave function for an electron in an atom does not then describe a smeared out electron with a smooth charge density. The electron is either here or there or somewhere else, but wherever it is a point charge. And I think it's quite interesting to look back into this, because now when we do experiments with laser light of the type we did, we saw in the experiment that this is not really the case. We can really think about electron as a smeared out charge density in some cases, but not in all. And that's where things are a little bit weird. So let me show you the opposite case. Here is an experiment where thinking about the electron as a smeared charge density gives us incorrect results. Okay, this is an experiment that was done in Adi Ari's group in Tel Aviv University. And that's a scenario where we cause the electron to emit light in a slightly different way. We have an electron interacting with a grating structure. That is a grating structure that is causing the electron to emit radiation a bit like an antenna array. And what we do is then broaden the electron transversely. The electron is wider in space in a way that causes it to act, if it was a semi-classical distribution, to choose between two options. Either the electron emits as a wave function, like it did so far in a previous experiment I showed, and then the radiation is expected to be directional, to interfere from different points in the wave function, or the electron distribution is actually a probabilistic effect, and then we need to randomize where it is every time and ask where is the radiation going. And the radiation pattern is different for those two descriptions. So we can really tell apart what's happening. And what is clearly happening in this experiment is that the right picture is the correct one. The electron is first collapsing into a point and then emitting radiation. So that the description of the type of a time-dependent Schrödinger equation, for example, will give us nonsense results. And that's a very important thing to see here. So that's exactly the opposite case. That's where the electron first collapses and then radiates. That will describe the experiment perfectly. And I think that the fact that those two pictures are so different is something that makes us interested in this whole field. And I want to say that it's all in the end explained by the fact that the electron is partially entangled with the radiation. Okay, it depends on the radiation it's entangled with and what are the modes it's entangled with. But that picture will capture everything. And it's important because there is no open question in the Gedanken experiment, or at least not one I'm aware of. Everything we have faced so far, we can analyze rigorously with quantum electrodynamics, or more specifically with macroscopic quantum electrodynamics. Because what we need to do is to capture here the details of the interaction. For example, what is the optical environment? What is the mechanism by which the radiation is emitted? When we take that environment into account, and you can read more about MQED, there is a really good review that was on archive for years by Schill and Buchmann, that has hundreds of citations by now on archive. There is also a more recent one that we had a month ago in Nature Reviews Physics. And MQED is also, this review was based a lot on the class I taught on this. Now, when we use that QED with the macroscopic environment, we can explain all of those experiments. And still, this Gedanken experiment leads us to new ideas and physical phenomena and applications. And I think I'll use the last 2 or 3 minutes of my talk to show you 2 such examples of the kind of ideas that come up from describing this Gedanken experiment. And for this, we can look at the following scenario. This is work led by Chen Michel, who has also presented the very first steps on this in a retreat in physics. I think it's about 2 years ago. And the idea we were curious about is whether we can use the electron that gets entangled with the light it's emitting in order to quantify the light, in order to learn something about the material. It's tool in microscopy. And think about the following scenario. When the electron interacts with some sample, let's say a thin surface of metal, it can cause electron fluctuations on the surface. It can excite electron waves like plasmons, either surface plasmons or bulk plasmons. And then that electron that flies through lost some energy. And now we can ask whether this electron can still interfere. What happens when we send this electron through a double slit apparatus and look at the interference? And what we find is not too surprising maybe, but it's still, I think, quite peculiar and interesting, is that when the interaction is with a mode that is very localized, like a very lossy plasma, then the electron cannot interfere anymore. However, when the mode it interacts with is not very localized, so there is a mode on the surface that is delocalized, like a low loss plasmon, then the electron can still interfere, even though it already went through an elastic collision and already lost some energy. It did not collapse. And that's exactly modeled when we look at the entangled state of the electron and the excitation, and then ask whether that entangled electron can still interfere. Now, mathematically, we can write that explicitly. We can ask what is the density matrix of that electron that hits the screen. That density matrix for each electron energy depends on what energy loss it went through. Has, if we look into the full density matrix, so it's a function of R and R tag in the transverse screen, is described by an integral on the imaginary part of the green function. And I think that's a really beautiful relation, because we see that the density matrix of the electron is directly connected to the green function, to the electromagnetic green function on the right side. And through this interaction and match, we can really connect the non-locality of the electromagnetic mode to the non-locality of the electron. And we can use that, for example, to extract information about plasmons, to find the plasma dispersion. And I think I'll jump over this because I want to mention one more thing. And that's another example of what we can do when we have our electrons interact with some medium. So consider what is the radiation from a classical point electron, something where the source, the current, is the delta function of a point charge moving with some trajectory, whether it's a case where the electron is a wave function. So that now the current is an operator where the wave function operator is deriving that. And those two examples will emit potentially very different kinds of radiation. And that's a question that is following us for quite a while. But let's think about it in the inverse. If we measure that radiation, what can we say about the electron? And whether, for example, we can say some new information about particles in high energy physics, or design some high energy physics detector, like the ones that are used in many experiments today in CERN and in cosmology and other places. Can we measure the radiation from the particle to infer something about a particle? Can we say what's the extent of the wave function, whether it carries some orbital angular momentum? What other information can we extract about particles in high energy physics from looking at the radiation they emit? And for this, Aviv Kornieli, who's a shared student, co-advised by Adi Elia and by me, designed this really beautiful idea of how to do a quantum optical measurement. This looks a lot like a homodyne detection scheme for the light emitted from a wave function electron, and then how we can extract the information and actually reconstruct, like in quantum tomography, everything about the wave function of the electron. And this is generally leading us to this ideas of whether quantum optics and detectors of this type can be used to improve detections of properties of particles. We have a lot more to say about this, but I think I'll not jump further into this. Instead, I'll conclude and leave some time for questions. I think this can also wait for another day. Yes, and I'll end with this slide with a picture that took us along the talk, and I'm glad to take questions. Also hear your thoughts and continue this discussion forward. Thanks, everyone.
Thank you, Ido. Thanks for the interesting talk. And thanks. So yeah, so we do have some time for questions. Please just unmute yourself and ask.
Ido, I have a question in the comment. first I must go back to your reference. First, I must commend you for really making big progress in the understanding of the interaction of shaped electron wave function with radiation and with matter now. But this work on interaction of electron with matter, or what we call free electron, bound electron resonant interaction, was published already 2 years ago. And it was a semi-classical analysis. The quantum analysis was published by us more than 2 weeks ago, and I sent you a copy of it. So I must express my surprise that you don't mention this reference along with the other 2 references in archives that you mentioned. So I hope that you will correct it in the future.
Yeah, this is a very recent work that is worth mentioning all of them together. I think that, and you're right, I think that a semi-classical description is the one that really started a lot of the interest in this direction. And if I had given a talk about interaction with qubits, I would definitely be going through this. But it's also a very complicated topic to bring up because it's very controversial of to what extent the semi-classical description is legit and in what places it fails. Right? And I think the important thing about this work in PRL is that it is the first one to suggest doing that. Even if today many people will say that it's not describing reality in many cases because it's semi-classical, it's still the first one to do it. So pros and cons, but it's not the core of this talk. And you're right that other archive is also important, and I should have added that.
The other archive is not semi-classical, it's fully quantum.
Yes.
And really,
I believe so. I just didn't have time to go through it as well. But it's probably
okay.
right.
So I want to put it, having said that, I want to put it aside. The capabilities of your system are really extraordinary, and you can do all these experiments in addition to this nice theory. You can really demonstrate all these experiments in the triangle that you showed. That's a great opportunity. I have questions though about the experimental realization. Everything that we measure has to be done with many electrons, even though you emit electrons one by one. But at this point, the electrons are emitted from the cathode, and you don't know at what shape they are. What is the inherent, the wave packets are coherent, but you don't know how they are emitted. And you know that they are expanded because of the inevitable chirp of electron wave packet propagation in free space. Just a moment, I'll also video myself because maybe you notice that I turned off the video. So the questions that I have, if you paid attention to the thought, how to control the size of the wave packet, it's not an obvious thing experimentally. You should be able to chirp the electron and do some processing in order to get the wave packet at the right size, because it showed long wave packet, short wave packet, with chirp or without chirp. Do you have any thoughts how you are going to manipulate the electron wave packets experimentally?
And there are several papers by other groups in the field looking into how to manipulate electron wave functions. In the transverse directions, it's relatively straightforward with magnetic lenses, for example, and with other methods as well. In the longitudinal direction, people can use cavities, RF cavities, microwave cavities that will modulate and squeeze or stretch the electron in time. And that is typically applied on classical electron distributions, but it should also apply on electron wave functions in a similar way. And I think those are the most standard ways, but you can also use the shaping of the laser to do that potentially. So there is a lot more to do there. We are right now modulating the electron into an attosecond comb, into this train of electron peaks that's with the interaction with the laser. That's also an option. But I'm sure there is much more that will be done in the next few years on this.
Do you have the option to do it like Peter Baum is doing it with a terahertz modulation?
Probably, if we bring the right terahertz source, and this is something we're thinking about. And I can discuss much more, but I think it's better to discuss this outside of this forum.
Okay, thank you.
There's a question by Asa Auerbach.
Hi, nice talk. I have a question, actually two questions. First of all, the wavelength of the electron is extremely short, right? You're not anywhere close to seeing the wavelength of the electron. So
right.
when you talk about the
here is a few picometers.
Right. So it does look like it should behave like a point particle relative to slow potential fluctuations. But so the question I have actually is different. When you look at this graph of the sine frequency with a periodicity of omega, it's a Fourier transform of like a two-time collision. As you said, it's like a two-slit experiment. But I haven't seen in the experimental setup, what are these two times?
So actually, if you have calling it a double slit is a little bit of a simplification, because if you have, if we have more than two slits, like a grating even, right, a set of slits, you will also see this interference.
No, then you'll see Bragg peaks, like in solid state physics. Then you'll see sharp delta functions. What? Right? This is a typical two-slit periodicity, right? If you had if you had a lattice of points in time space, you would get a lattice of points in frequency space.
Yeah, and those lattices are just a little bit broad. So what we see here, this is the energy, what is here at the top of the screen, is the Fourier transform of this will be a periodic field as well. So we are actually Fourier transforming lattice to lattice.
Like you have two times, which are exactly separated by 2 pi over omega, that the electron hits something at one time and then again at this time spacing. So I wonder if this setup that you have can explain it. I don't know.
Yeah, if we are, you're right that the actual shape of this that we get here is not exactly straight, right? When you zoom in enough, it looks very straight, but when you zoom out, you see it has more complicated shapes. And I think
it does look like a perfect sign to me, but maybe I'm...
Yeah, it's just because it's zoomed in, I guess. I think that we shouldn't think about the interaction as just 2 points in time, because it's more complicated. And then the picture in energy is also more complicated. And just when parts of it look a lot like double slit, but in general, there is a complicated wave function for the light, and then it translates on a complicated wave function for the electron.
Okay, thank you.
That's
Okay, so there's 2 more questions. The first one is by Yotam Sorek.
Ido, you mentioned very briefly at the end the implication for high energy physics detector. Can you say a bit few more words, what you have in mind? In which type of detectors?
So the most natural for us to think about are Cherenkov detectors. We actually put this slide a bit more, because why Cherenkov detectors? Because Cherenkov detectors are the most natural, where a particle comes in and emits light, and we measure that light. Right? And that light emission is done in a very well-known way. It's also the same theory that we are using here anyway. So what is a Cherenkov detector? Normally, it's the electron or any other particle is emitting a cone of light, and we measure that cone. We measure the angle of the cone. The angle of the cone tells us what's the velocity of the particle, right? You know that better than me, but I'll see it for the rest of the people here. Now, what we normally measure is the angle, and then we can say the velocity. But what if we want to know much more? Let's say we think the particle it has some distribution in space. That distribution, we don't know whether it's a random distribution that's classically, stochastically random, or is it a coherent distribution, because the electron is actually, or any particle, is actually coherently broad. How do we tell what is the coherent width of this? So normally in a Cherenkov detectors, we will not be able to say this if we only measure the intensity. But if you look at correlations, and that's where quantum optics comes in. If you look at the correlations of the particle, of the light with itself, for example, here, modulate part of it, interfere it with itself again, you can extract an additional information about it. And
Okay,
for
I see.
example, the size of the wave function is the first thing we're interested in seeing.
So in many times, Cherenkov radiation is used to distinguish between, for example, pions and electrons. Did you try to play with a different type of particles with this system? For example, muons or electrons?
We have a
Simulation.
Yeah, we actually have a series of projects, and one paper from 2 years ago on building nanophotonic detectors. So you can change the bulk medium by something more complicated. And then we definitely also place different kinds of particles, including muons, pions, kaons, protons, and ask what is the different angle you get. And there are ways to use ideas in nanophotonics this way, to design a more complicated metamaterial that will improve detectors. That's something we're still thinking about. Here, the proposal is a bit different. I'm thinking not necessarily about telling apart the particles, but about a single particle we already detect. Can we say more about it? Can we extract more information about the particle that is, normally we don't think about that kind of information. That's a new idea. I mean, that's not published yet. It's on archive from the last 2 weeks as well.
Okay, maybe we discuss it offline because I will try to ask you a few questions offline because there's no time. Thank you.
Okay, so there's a question by Lev Weidman.
I enjoyed very much the talk, and I have seen very interesting experiments, but I have doubts about, you presented in your talk that it has a relation to interpretation of quantum mechanics, at least you hinted for this. You talked about that we study collapse of a wave function of electron. And so it looked like there is a question, what will be the result of experiment if there is a collapse or there is no collapse? And it seems to me that this experiment don't tell us anything about collapse. It's very difficult, probably impossible to test if there is a collapse of the wave function, because this experiment clearly will not see the interference because of entanglement. In this cartoon of two-slit experiment, that clearly the electron which emitted photon from one slit is orthogonal to the quantum state of an electron emitted from the other one. So with collapse or without collapse, the interference is impossible. In the other experiment which you showed, when the electron remain in the same thing and you were not entangled with the emitted photon, then we can see interference. So I think during the talk you didn't make strong statement. You said that you can explain it in any way. But what I believe that everything can be explained by just pure quantum mechanics with any collapse and just by entanglement between electrons and emitted light. So
I completely agree with your bottom line here. And I also said the same thing, that we can explain all of those experiments with the entanglement of the electron and the light that is emitted by it. I don't agree with the fact that this experiment will always show us no interference. I think that there could be scenarios where those glowing points here can actually create modes of light that will be overlapping in some way, where the final electron will be overlapping as well. And then you can get scenarios where they will actually interfere. But that requires breaking what you said, that you said they're orthogonal. As long as they're orthogonal, it will indeed be no interference. But if the electron can excite a mode where at the end of the process, the final electron state will not be orthogonal, then the light will also be able to interfere or partially interfere. So I don't think it contradicts. I think that we can get scenarios like this that are interesting scenarios. And there is even one experiment that showed something like this indirectly. There is an experiment from Belgium that looked into an electron that was also modified in shape, interacting with a surface where plasmons were having some symmetry to them. And over there, by post-selecting the electron, which is slightly different from what I did here, you can see the interference of light, or you can see something that looks like it on the electron. Right?
Sure. Well, when you post-select, if you are able to post-select the electron, then of course, then you can post-select on particular state of the electron, and then you will see interference. This is this is
So let me show. And we thought for a while, we thought for a while that, yeah, as long as we don't post-select, we'll never see any interference. But actually, we found scenarios where this does interfere, even when you trace out everything.
Yes, but not as your picture. In your picture, the electrons are separate in space when they emit. So without post-selection, you will not see interference. When the electron is not in different location or something, when it's then just different shape or something like this, then it might be possible.
Yeah, so you mean that we need to have some way for the electrons to not be orthogonal.
Yes.
I completely agree. Yes, but they could be in different places in space and then through the interaction get overlapped. For example, be scattered to the same location.
But then you have to post-select on them. If during the emission they were orthogonal, end of story. Until you make post-selection of an electron, you will not see interference.
So, let me show you one case where this may challenge it. If what we're doing here is looking at Bremsstrahlung. Okay, there is an atom. We took a carbon atom for the model, and you can either look at a single electron plane wave scattering by it, or look at the interference of two plane wave electrons. So they are clearly orthogonal. And still, what we thought originally is that when you will have two orthogonal two plane wave electrons interfering, the relative phase between those two electrons, let's call it 1 and 2 here, the relative phase between them will not matter to the radiation. And still, when you have an emitter like this, that breaks symmetry in space, that allows the final electron states to overlap partially, and it gives you this like a pattern of radiation, and the coherent or the incoherent addition of them will give you a different pattern, a very different pattern. So if you tailor the scenario so the final electrons are not orthogonal, you can have the electron wave function alter the radiation emission. But you're right that we need to tailor it so the final electron states will not be orthogonal.
Okay. Thank you.
So that's why we need to work hard to fight entanglement if we want to see any interference. I think we agree on this. The question is only how to do that.
Yes, thank you.
Thanks, Lev.
Okay, there's at least one more question, but I suggest, given that we're well over time, I suggest that we officially thank Ido for this very interesting talk, and then whoever wants to stay informally and ask more questions, let's do that. So thanks a lot, Ido.
Thanks, Daniel. Thanks, everyone.
Thank you.
Yeah. So Lev, you're right that we're still trying to find the experiment that will have no post-selection, but only trace out, and that will be a way to see this in a more elegant way, I think. And that's but even let me be my own devil's advocate for a moment. Even if we find that, this is still not something that is challenging the picture of what is the collapse of the wave function, right there. I think
you can see experiment when there will be no complete full entanglement, and then you will see some interference. But to test the collapse, there is no. But of course, it helps to thinking if it's charge density or not charge density. But again, if you just use quantum mechanics and entanglement between photons and electrons, everything works.
I think what I want to see is something more. That's why I asked you when we met before Corona. We met briefly, and I think that all of the experiments we have here so far can be explained with the entanglement and cannot challenge the question of what is the worldview of what is the collapse, right? There is no, I don't know a single experiment that can tell apart between.
And I'm very sure that it's no chance to have one.
Yeah, and the problem is probably there is also no way to have one. But that's what we hope to see, right? The most exciting experiment. The reason we're playing with this in the first place is the hope to have an experiment that will be able to tell apart the pictures. That will be the most exciting thing ever, right? That's the reason to play around with it in the first place.
If we will see that some collapse happened and quantum mechanics breaks down, this will be very exciting and very unfortunate for me. I don't believe quantum mechanics is the final word of nature. Till today, we don't have any signs that this will happen.
So in some way, what I hope to do the experiments that have a chance of doing something that do not agree with theory, right? That will be a regime that is most exciting, I think. And that's why we're playing with those type of experiments, but we don't have the one that can tell apart, oh yeah, it's many world versus other pictures. I mean, I don't see a way to do that right now. And we hope to find some kind of experiment of that type. And that's why we are playing with those kinds of experiments in the first place. Now, it may be that collapse will just be, the entanglement, QED can explain it in a standard way. And there are still some surprises there. I think that much of what I showed here is still, people call this collapse, even though you don't have to explain it with collapse, for example, right? That's, maybe in 20 years, this will not be the term to use anymore. We'll just say entanglements for all of the experiments I showed here.
I want to believe that that pretty soon will be consensus and people will forget about collapse and will just use quantum mechanics. Still, we can use it and find interesting effects, even quantum mechanics without collapse, even without kind of new physics. Still, the sprint post-selection, I think at the end you said that you make some post-selection and then you can get effective, interesting interaction and you can see interesting.
Yeah, I know, but and I said the word that was also, the post-selection is making this different. But see, there are things that are surprising us, even though we think we know it. For example, here is the simplest. I think the one I like the most here is this here. Right, there is this very simple picture. We think about an electron going through a medium. It's emitting light in the form of Cherenkov radiation. We call it a shock wave of light. Right? We call this. Why do we call it a shock wave of light? Because it's emitting a lot of different frequencies, and we are thinking about those frequencies as solutions of Maxwell's equations. Since there is a broadband source in frequency, in the time domain it will be very narrow and short. But if you think about it as an entangled photon, a set of possible photons, each entangled with the electron, each photon, each color is going to be entangled with a different electron energy. So how could it be that the photon colors will interfere with one another? According to the picture we just said, there is no shock wave, right? The different colors cannot interfere at all.
No, but if electron in the beginning had uncertain energy, then they can easily interfere.
Yeah. Perfect. So actually, what we're saying is that the ability of a shockwave to form depends on how much uncertainty the electron had in the first place.
Yes.
This is how I should answer. I should have answered your Tom, because that means we can, by measuring the duration of the shock pulse, can tell what is the uncertainty of the electron energy. Right. That's a really elegant connection. And in practice, by the way, the electron uncertainty energy is tiny. It's very small. It's very disappointing, actually. And that means that I don't think that any experiment so far that saw Cherenkov radiation ever had a shockwave there. Since 1934, people say, yes, Cherenkov is a shockwave of light. Even I say that in talks. But actually, I don't think it was ever a shockwave of light, except for maybe someone managed to make a very uncertain electron somewhere. But when we make them in our system, which is relatively impressive in its coherent width, I don't think it even gets to 1 eV. So there is not much uncertainty in the electron. So there is no shockwave of light, for example. That's a very simple statement that comes from this understanding of the entanglement of the electron and the wave, and that I think is quite surprising.
Yes.
Ido, may I ask you a question about this slide? First of all, there is no shockwave picture ever in Cherenkov radiation because it is indeed not the electrons that emits the light. It is a polarization that it creates in the solid around it. And this has some relaxation time, so we should take it into consideration.
I mean, how quickly polarization of the medium can react. But medium polarization can react on femtosecond timescales, right? Not much shorter than that. So it's not going to be not an attosecond shockwave, but a femtosecond shockwave should be possible, all the way up to picoseconds or so.
Also, you can do it with Smith-Purcell experiment instead of a Cherenkov experiment, and then you have conductor. But I have another question. What matters?
I'm sorry to interrupt. It's just that Ofer Neufeld has been wanting to ask a question for a long time. And also, Ido, I'm sorry, I have to leave, but thank you very much.
Thanks, Daniel.
Thanks.
Yeah.